Hello. Today, we will be looking into the production of frozen yogurt ice cream, Fro-Yo. My name is Josh Miller, and I am joined today by the members of my group, Keelan and Albert. Our group was tasked with coming up with a process and/or product that could utilize fermentation to make a product. Our group decided upon high-protein frozen yogurt due to our love of physical fitness and interest in healthier food products. With the growing trends of the need for high-protein, low-fat frozen yogurt, we believe our product will make a great addition to the market. In order to obtain a product that would be high in protein and low in fat, we'd utilize ultrafiltration in order to filter out all the fat particles and leave the high-protein content. When designing the frozen yogurt, the three parameters we decided upon were a combination of taste, texture, and nutrition. It is important to note that since this is a food product, safety and other health considerations are vital to the process. In order to get a better understanding about the process of making this frozen yogurt, let's take a closer look about who Fro-Yo is. Fro-Yo is a privately owned and operated company located in Hillsboro. It has a trademark recipe that is specific to our company alone. For this plant, located in Hillsboro, our target production rate would be about 6% of the market share by the end of the 10-year lifespan of the plant. At this production rate, we'd be able to charge $1.90 per ounce of serving. The biggest selling point of Fro-Yo is its high-protein, low-fat content, which is obtained through its ultrafiltration process. In addition to the ultrafiltration, probiotics can be added to the frozen yogurt in order to improve the nutritional benefits of it. The homogenization of the milk allows for the yogurt to have a fantastic texture along with a great taste. According to Dairy Herd, around 80% of Americans prefer frozen yogurt to ice cream, gelato, and other frozen treats. Most other frozen yogurt products contain around 4 grams of fat and around 5 grams of protein. Our process, utilizing ultrafiltration, will contain around 7 grams of protein and 2 grams of fat. Our process, utilizing ultrafiltration, will contain around 7 grams of protein and 2 grams of fat. There are a wide range of possibilities when it comes to the potential flavors of the frozen yogurt. The three most common types of flavors are strawberry, vanilla, and chocolate. However, in our group, the favorite flavor was cookies and cream.
Before creating Fro-Yo, a market analysis was done to determine if there was any room for our product to flourish. Through research, it was observed that yogurt sales are expected to increase by 58% by 2022. As a result, we took advantage of that and the fact that the fitness world is still growing to find our place within the yogurt world by creating a healthy and delicious frozen yogurt product that can be used both as a post-workout supplement and snack. As college students, we felt like it was easier for us to connect with a younger crowd because we have interactions with a diverse group of young people on a daily basis through USF's student population. As such, we wanted to exploit that resource of having access to a large population of people on campus who are physically active and target a population from ages 18 through 45. Within this group, we have fitness enthusiasts who are regular gym goers and athletes that compete, undergrad students that participate in any sort of physical activity, whether it's cycling, lifting weights, or playing sports, to name a few, as well as health-conscious adults who care about their health and what they eat. In the early stages of our research, it was observed that 121 million yogurt products are produced per year in the United States. To determine our position within the yogurt world, we assessed the market by comparing the top frozen yogurt and Greek yogurt companies by market share, existence, and protein content. Companies included in our assessment consisted of Menchie's, Yoplait, Orange Leaf, Yogurtland, Chobani, and Sweet Frog. Most importantly, we factored in our potential buyers. Firstly, by comparing how long each company has been in existence, we estimated by year 10 of operation, Fro-Yo will be able to produce 6% of the 121 million yogurts produced. Secondly, because we had access to our demographic at our disposal, we integrated their feedback to create Fro-Yo's main selling points. We asked USF students what the top 3 things they were looking for when purchasing any type of yogurt product. We then based Fro-Yo's creation on these factors. These factors are price, which was aforementioned, nutritional facts, and taste. Nutrition is the greatest driving force for Fro-Yo, mainly the amount of protein per serving. Lastly, Fro-Yo was compared to our competitors by protein content. For instance, Menchie's, the largest frozen yogurt company, acquires 13% of the market, and their yogurt has a protein content of 4 grams per 150 grams of yogurt, whereas Yogurtland has 2.9 grams. Chobani, the largest Greek yogurt company, has 14 grams, Orange Leaf 1, Yoplait 11, and Sweet Frog 3 grams. Taking this into consideration, Fro-Yo will have 17 grams of protein. Due to the current trend with promotional tools, we opted for a cheaper alternative to promote our product. With social media's grasp in everyone's hands via smartphones, we wanted to take advantage of that and utilize the platforms of Snapchat, Facebook, Instagram, and YouTube as our primary methods for promoting Fro-Yo. The use of social media, famous fitness athletes, is also a great inclusion. It is common for many famous fitness-oriented people to advertise products on their pages to their large and diverse fan bases. The greatest and inexpensive promotional tool Fro-Yo has is the use of pop-up shops. With the USF's population at our disposal, we can use the culture of bull market and promote around various college campuses in the state of Florida by providing samples of Fro-Yo in exchange for a like or follow on one of our social media pages to increase awareness and get instant feedback from our targeted audience. At our campus, for instance, Bull Market is an event that happens every Wednesday at the Marshall Student Center, where most students populate. Tents are provided for various organizations to promote their products and events. Moreover, since our Fro-Yo is being branded as a post-workout supplement, advertising at all fitness facilities on campus, such as USF's Campus Recreation, the Fit, and the Well, is of paramount importance. Showing face at various fitness events all over campus throughout the year, from intramural sports and the Rec Fit Games, will also be a great asset in promoting Fro-Yo. An economic analysis was done to determine the economic feasibility of Fro-Yo. For the early stages of our plan, we utilized a net present worth calculation using the criteria that our plant was feasible if the NPW was greater than 0. We used a plant life of 10 years. The price calculated from it was then used in a return on investment calculation. The price was determined to be $1.90 per ounce. Based on these initial values, an ROI of 15% was calculated and our plant was deemed feasible with a payback time of 5 years. This can be seen graphically from our cash flow diagram. A discount rate of return was also calculated with a value of 25%. It is important to note that there is room for improvement with these values. Further calculations will be done to achieve a more profitable plan using tools such as a Monte Carlo simulation. Our goal is to reduce the price of Fro-Yo per serving as well as our cash expenses.
This slide is a general overview of the overall process of the production of Fro-Yo. The process starts out with the arrival of the shipment of milk that is placed into a holding silo. From there, the milk is put through an ultrafilter where it takes out the fat and leaves the high protein content milk. From there, the milk is sent to a pasteurizer where it is heated to 82 degrees Celsius for around 30 minutes. This process not only kills off the harmful pathogens and biohazardous materials, but also allows for partial hydrolysis and the inactivation of the immunoglobulins in the whey protein. After the milk has been heated in the pasteurizer, it is sent to the homogenizer to ensure proper texture of the yogurt. From there, the milk is sent to the fermenter. The fermenter is the most vital step in this process. During fermentation, milk is combined with Streptococcus thermophilus and Lactobacillus bulgaricus in order to ferment it. This fermentation process turns lactose into lactic acid and overall lowers the pH of the milk. Once a pH of 5.5 is reached, the fermenters are cooled to around 7 degrees Celsius in order to stop the fermentation process. From here, the now yogurt is combined with cream in order to give us our frozen yogurt mixture. It is also added with flavors and probiotics to improve the overall quality of the frozen yogurt. From here, the frozen yogurt mixture of yogurt and ice cream is sent to a scraped surface heater where it will cool to around negative 17 degrees Celsius and start to freeze. From here, the frozen yogurt is ready for storage and shipment. It is important to note that during these last steps, the frozen yogurt must remain at around negative 17 degrees Celsius in order to inhibit growth of bacteria and other biological hazards.
As seen in this chart, there are 4 membrane separation techniques utilized in the dairy industry, each possessing its own set of characteristics, such as the required driving pressure and pore size. Reverse osmosis is used for milk dehydration, nanofiltration for partial desalination of milk, ultrafiltration for protein standardization of milk for cheese and yogurt, microfiltration for bacterial reduction in skim milk, and also for defatting whey for whey protein concentrate. The permeate in an RO system, like that used to desalinate seawater for drinking, is normally the desired product, while in an ultrafiltration system, the retentate is often the valuable product in the dairy industry. In the nanofiltration range, lactose and minerals will also be filtered out, which is undesirable because the cultures in the fermentation stage of the process feed on lactose to produce lactic acid. As such, our process uses spiral wound ultrafiltration membranes to collect most, if not all, of the protein content in milk in the retentate. This table shows all the proteins found in milk. In all, they account for 3.24 weight percentage of 3.6% fat milk. The key proteins in milk are the caseins, alpha-lactalbumin, and beta-lactoglobulin. Because of their larger size, caseins are easily retained by ultrafiltration. To know the rejection coefficient of a semi-permeable membrane, the molecular weight of the solute, or in our case the protein, is required. Also needed is the molecular weight cutoff of the membrane, which represents the molecular weight of the protein that will give a rejection coefficient of 0.9. Using this equation, we can find the required molecular weight cutoff of the membrane to be used in the frozen yogurt process. Using 28,000 Daltons, it is found that a membrane with no greater than 15,000 Daltons is required to reject 90% of all protein in milk. To ensure that all the proteins are collected, we use 10,000 Dalton membranes, which is a common industry practice. As mentioned earlier, in a reverse osmosis system, where the filtrate is 99% water, a single pass operation is sufficient. However, the protein content in the retentate is desired in a dairy processing plant. A single pass operation would yield to relatively large amounts of wasted filtrate. Furthermore, a very long membrane path or a very large area would be required if, for instance, the desired concentration factor is 6, which is used for protein concentration in cheese production. However, because yogurt does not require such a large concentration factor as that for cheese making, we nevertheless decided to use a single pass operation due to the batch nature of our production. The right amount of protein content in the retentate is achieved when varying the flux of the permeate in the milk feed. According to the polarization flux model, the flux ranges from 30 to 120 liters per square meters per hour, depending on several key variables, such as transmembrane pressure, intrinsic membrane resistance, osmotic pressure, wall concentration of solute, and membrane fouling resistance. A homogenizer is useful for creating an evenly textured and more full-bodied yogurt, and thus has become widely used in yogurt production. Such machines turn fat globules into much smaller ones, so that clumping or coalescing may be reduced. This is done by forcing milk through a small passage at very high velocity, such that cavitation occurs. The larger fat globules disintegrate due to turbulence and cavitation. On average, fat globule size is reduced by 2.5 micrometers to 1 micrometer. It is critical for the temperature of the feed to the homogenizer to be not cold, that is, below 40 degrees Celsius, lest ineffective homogenization will occur. In most cases, proper temperatures range between 55 and 80 degrees Celsius. Pressure should be at 200 bars with a pressure to the pump of 2 bar.
The fermentation process is one of the most vital processes in the production of frozen yogurt. During fermentation, milk is combined with Streptococcus thermophilus and Lactobacillus bulgaricus in order to ferment it. Most fermenting techniques use cold culture growth due to its high leading biomass yield, then separate using single-strand culture because of the proto-cooperation between the two species. A model designed by Dr. Tamine and Dr. Deeth was used in order to describe the reaction between the cultures and the milk. During this reaction process, there are thousands of different side reactions that happen. However, the main one is that lactose and lactase is turned into glucose and galactose. From there, the cultures turn that into lactic acid. This gives the yogurt a thicker texture and viscosity, along with lowering the pH of the overall substance. From the models and data, the optimal time for the fermentation process is approximately 6 hours. For the purposes of this design, it will be assumed to be exactly 6 hours, with a dilution rate of 1.86 liters per hour. The ratio of pounds of milk to pounds of culture should be 6 pounds of filtered milk for every 0.000857 pounds of culture. Once a pH of 5.5 has been reached, the fermenter is chilled to 7 degrees Celsius in order to halt the fermentation process. This is done through the use of a cooling jacket that surrounds the tank. The tank, which can be seen on this slide, has the capacity to hold 1,000 liters. This piece of equipment has a length of 1,500 millimeters, a width of 1,200 millimeters, and an overall height of 2,000 millimeters. It weighs around 1,000 kilograms. Since the end goal of our design for our project is to produce around 2,000 liters per day, we've decided that we would need 2 fermenters in order to run this process. The tank also includes an agitator that can run at speeds of 300 revolutions per minute. The tank is made of stainless steel, it is resistant to corrosion and abrasion, and is very easy to control the temperature. It is also fairly easy to install and operate. On this slide, we can see the overall process of the vapor compression refrigeration cycle. This process is vital for our production of frozen yogurt, since maintaining a constant temperature is key. This allows us to control the growth of biohazards and pathogens, as well as control the texture of which the yogurt will flow through the system. While designing this process, assumptions need to be made in order to model the system. However, key assumptions were made that need to be listed. The first assumption is that the milk into the system equals the mass of the exiting yogurt. What this is basically saying is that during the fermentation process, all the milk gets turned into yogurt, and at no point during the process does the milk get spilled into the environment. The second assumption, which is key for this process, is that the skim milk is 90% water, so it can be assumed to have physical properties similar to that of water, such as density and viscosity. This plays a vital role when it comes to designing pieces of equipment such as fermenters and ultrafilters, since the flow properties of the liquid flowing through them dictate a lot of how they're designed. It is important to note that while the density and viscosity can be modeled after water, there are still contents in the milk that affect how it flows and how dense it is.
To minimize the risk of foodborne illnesses, the Food and Drug Administration has adopted a program known as Hazard Analysis and Critical Control Point in different areas of the food industry. This is done to reduce the food safety hazard and is facilitated by procedures such as pasteurization. The FDA does not currently require the use of the HACCP as a food safety standard for the dairy industry, but there is voluntary HACCP in that it is used as a model for safety assessment. Since frozen yogurt is a milk-based product, it is a good medium for growth of microbes at different stages of the process due to the high nutrient content, favorable pH range, 5.5, and long storage period. There are pathogens that have the potential to grow at any stage of the process in the frozen yogurt. This can be prevented by controlling the environmental conditions to inhibit growth. The three areas that can restrict this growth of the pathogens are the pasteurization, fermentation, and the cooling stages.
Pasteurization is typically the most used application of heat treatment in milk products. The key factors that help accomplish restriction of growth of the bacteria are time and temperature. In this process, ultrafiltered milk for making yogurt is heated to 90 degrees Celsius for a period of 30 minutes. This heating process kills approximately 99.9% of pathogenic bacteria in milk. This step in the process is critical because it limits the potential hazards in milk to acceptable levels by the International Dairy Foods Association. The fermentation step in the process is the next critical step for eliminating potential hazards in the milk. During the fermentation step, cultures of bacteria are added to the pasteurized ultrafiltered milk to promote the formation of yogurt. This drops the pH of the mixture to 5.5 and increases the acidity of the environment. The increase in the acidity of the environment helps eliminate any other potential pathogens that might have survived the pasteurization step. This acidic environment not only prohibits the growth of harmful bacteria, but also helps prohibit the growth of other organisms competing with the lactic acid bacteriole for the available space and uptake of nutrients. Once the temperature of the fermenter is dropped, the fermentation process halts, locking in the contents of the yogurt. This fermentation process acts as yet another gate to harmful pathogens and bacteria. The cooling stage refers to the scrape surface heater where the frozen yogurt turns from a liquid mixture to more of a solid with flow properties similar to that of ice cream. During this step, the mixture is cooled to negative 18 degrees Celsius and is kept at this temperature during storage and transportation. While it is feasible that some bacteria can survive the freezing process, the extremely low temperatures do not promote any more bacterial growth, eliminating the potential of new bacteria in the system to grow. It is important to note that if any bacteria survive the pasteurization, fermentation, and cooling stages, they can become active when reheated by the human body during consumption. Each of these processes acts like a gate to help prevent biohazards and pathogens from remaining in the frozen yogurt. The safety of the product is vital since consumers will be ingesting the frozen yogurt and will be susceptible to the most risk. It is important to note that even if these processes are monitored closely, harmful pathogens can still enter the product outside of the process. For instance, frozen yogurt has the potential to be contaminated even after leaving the manufacturing facility through transportation and shipping, if good manufacturing practices are not followed or proper temperatures not maintained. It is vital that proper hygienic and sanitary practices are used when loading, unloading, and inspecting the frozen yogurt. It is also important that the temperatures of the frozen yogurt is maintained at negative 18 degrees Celsius to prohibit bacterial growth. There are also hazards to the employees who are operating the equipment and working in the facility. Some heat exchangers utilize ammonia to cool the process down. It is important that if any spills happen, nobody inhale the ammonia. It is also important to note that while it is not a big hazard, there is some whey acid that people should avoid contact with the skin. Lastly, workers should avoid at all costs ingesting any of the cultures, since these cultures thrive in an acidic environment and can cause potential health problems for anyone who ingests them. While designing this process, there were several steps along the way that could have been improved in order to increase production rate and price point. Since the fermentation step takes a total of 6 hours in order to complete, this can be sped up by the use of multiple fermenters. While one fermenter is fermenting the milk, the other is being cleaned and filled with milk in order to be fermented again. Another way we can optimize this procedure is by finding the right combination of permeate flux, milk feed flow rate, and protein percent content. By adjusting these numbers, we can reduce the amount of milk we waste during the ultrafiltration step. Lastly, we maximize the quality of the milk by extending the time it's spent in the pasteurizer and lowering the temperature. This drastically improves the end texture and flavor of our end product, as it does not harm as many of the proteins and good bacteria that we want to remain in the milk. Some conclusions and recommendations we would have for this project would be to set the price point of the Fro-Yo at $1.9 per ounce. Another would be to have a scalable plant for larger capacity to meet the 8% total market share. During the ultrafiltration step, a lot of the permeate can go to waste. You need to reduce the whey permeate waste by using the multiple stage feed and bleed filtration system and by growing your own culture and using a recycled filtrate. Lastly, if you were to do this process on your own, creating your own ice cream mixture so it wouldn't have to be outsourced would be optimal. We would like to give some special acknowledgments to Kyle, Dr. Sonal, Ahmet, and USF campus recreational patrons. And our group in particular owes a special thanks to Kyle, because starting this project out, we were pretty worried about, a three-man group doing this, but he was able to guide us along the way and was a huge help in completing the process. We owe you a huge thank you for your patience and help along the way. So